Alright, time for another draftphysics.com, debatephysics.com also, video presentation. So something a little different, subject-wise. So motion in the universe is what's largely being discussed, okay? And I'm arguing that you don't need an ether, you don't need some bent geodesic. That what really runs the universe is this idea that there are just two things in the universe. There's electrons and protons, and I could show them as actually charged, but we're not going to bother with the explanation for charge in this video. We're just going to say there's basically a pushing force. So there's a force, little discrete bits of stuff in the universe, and that's what photons and all of that kind of stuff, magnetism, is made out of. Is these little bits of stuff, and when you put the little bits in a frequency, then it's a photon. When it's not a frequency, it might be gravity, it might be magnetism, it might be lots of things. Anyway, and so they have all the energy, so to speak. They're going the speed of light, and they're just little discrete bits, and there's bits flying through the universe from all directions. And what can happen is you put something in the universe, the electrons and protons, and they'll create different patterns of the bits. The bits will be changed in their pattern. And but that's all they can do, is change the pattern when a bit gets to you, not if a bit will get to you. So if something was in the universe, we'll just say this is a something made of mass, and the idea is that there's this energy coming from all directions, okay, and I'll just illustrate it as let's just illustrate it as just 2 bits, arrows. So they're just vectors, so little bits are flying through space, and they hit the matter and basically push it, because it's a push-averse. Can't pull anything, can only push or not push. And so the idea is something would be sitting in space, would be an electron or a proton, and they're just going to sit in space and do this. Yeah, they're going to be jostled by the fact that these little bits aren't organized in any way, and they don't show up at exactly the same time to every piece of stuff in the universe. So it's always getting, any one moment, it could be a little bit going this way, but it's going to be balanced because the universe is a big, giant, balanced mechanism. So anyway, so generally speaking, you have the same amount on each side. Now, if there's some gravitational body, like I said, that absorbs some of this energy, and that means there'll be a differential, and you'll be pushed into the mass. But let's just say there's nothing else in the universe but this one little object. And the point to be made is that there's a certain amount of these little bits, an infinite, gigantic amount of this stuff. So I could obviously put a whole bunch of arrows and make it more understandable. And if I move something, I can't really change how much energy it's going to interact with. So if we just said that every single one of these things reflected, that is, it hit, pushed the thing, and reflected, or it hit and stuck, you could sort of understand that if I moved it this way, a certain amount of stuff will stick, and I'll get to the stuff sooner. It'll stick sooner than it would have, but it's still the same amount of stuff. I can't change how much stuff there is. And so if I move this block, I'll move into more arrows here, and I'll have a bunch of arrows going this way, you could argue. And if I just sat here and waited a while, all of these arrows would catch up, right? Because that's the only thing I did. When I moved this way, all I did was I made these happen later and these happen sooner, but I can't change how many of them are. So the argument I'm going to make here is that the trick of motion in space, you could argue, is the fact that I can't change how much something's going to get hit unless, okay, I add another arrow. So if I did add another arrow, another piece of force from some direction, then you can understand that, well, I can't make that go away ever, really, right? Because it's part of the entire condition. And so there, even though I'll crash into this stuff sooner, because okay, I get this extra arrow, let's just say it's not moving, but there's one extra arrow coming this way. So that's going to cause it to move this way. The fact is all the extra arrow did was delay when you're going to get hit by, say, this arrow here. So by hitting with the extra arrow, you delayed when this one was going to hit because you moved it forward. But that one's going to show up. So this will equalize the extra arrow you brought in. You'll hit the amount of energy you would hit with that number, your motion. And then that extra one's going to show up again. So you never get rid of this extra arrow. You have to have an extra arrow from this side to get rid of it. You have to have something from this side that's going to create the little bit of extra that's going to compensate for that piece of extra, and then you'll stop moving. But you won't stop moving until this side can actually produce that extra arrow. It can't just delay it. Delaying it won't stop it from happening. So you could sort of understand if I did push this in without, if I pushed it into a force, a rain, a river, and I pushed it in, okay, and the idea is that now I've stored a bunch of extra motion. All I've done is temporarily stored it, in the sense that the stuff that I went ahead of is going to show up and equalize the pressure. The equalness can't be changed by time, I guess is what I'm arguing. The fact that you're moving into the force and you're going to hit it sooner doesn't change the amount of force. So the fact that there's an equal amount of force coming from this way and an equal amount coming from that way can't be changed by the motion. So you could understand that if I did move something into the force, that it's sort of elastic, in the sense that if I moved it a certain number of units with a certain amount of energy, that all of that pressure will exist over here and it'll just move it right back again if you gave it the opportunity, because it's going to regain that equilibrium. It's just going to recreate the equilibrium, the equalness. And so anything added, an actual added force, so that's if I didn't add a force. But if I add a force, then we know that all of this still exists. See, it's just a time thing. We get tricked by the fact that we think you can move something in space, and that somehow, the fact that this is a different time than it started at this time, that somehow that changes how much stuff was moving this way and versus how much stuff is moving this way. And it can't change that. Because if I could just hold it at that position, the other stuff's going to catch up. And it's going to equalize the pressure. So anyway, it's just an argument explaining why there is this idea of motion. When you push something and it keeps going, it keeps going because you've changed the balance, and the balance can't get unchanged unless you actually have an extra bit of energy over here. If the two sides have an absolutely the same amount of energy, and then you add one more to this side, it can't be undone by merely pushing into the other side. It's got to be undone by an actually extra bit of energy being added from the other side. You have to add the extra bit. And without adding the extra bit, you can't stop it. So I think it's a way of understanding that everything is in motion, but it's in motion in this construct of being constantly hit by a speed of light force. And you really do have to increase a force to create motion, and then you have to the only way you can stop that motion is to create extra energy from the other side. The elasticness of the field isn't enough to cause the reverse. It's only enough to stop something. It's not enough to reverse its motion, I guess you could argue. You can't, like I said, absolutely, it's not going to change how much is absolutely on one side versus the other side. Moving, if there's a certain amount of pressure and a certain amount of pressure, where you are can't change the absolute amount of pressure. Yeah. Alright, so that's part one. Yeah. go to part 2. Alright, back. So this is a draft video, frankly. Draft physics. Just going through the ideas and trying to find the best way to describe the circumstances that I'm attempting to describe. So the obvious argument from my perspective is, alright, this motion argument, that if the gravity is caused by a force, okay, so just as described before, there's an equal amount of force theoretically coming from both sides, and you could argue, okay, that what happens when there's matter is that some of the energy is absorbed and creates motion, so things move. And when they move, they're for a period of time using the energy. It's being used in the motion. And when they stop moving, then yes, they stop using the energy. So energy is just motion. So every time an electron or a proton moves, it means the force isn't going the speed of light anymore. So it's basically went from being something that's going this fast, okay, the force, when it's stuck on a piece of matter, it's only going this fast, right? It's going much slower than the speed of light. So it's diminished in when it's going to get someplace, and that essentially is the same thing as it being reduced in its capacity to do work. It can't go as many places. You see, if it's going slower, it can't do much. Going fast, it has lots of interactions. Going slow has very few interactions. Anyway, so the idea of a Lesage type gravity would just be the idea that there's a force coming from all sides, and the fact is that the force, okay, gets converted, you know, like the momentum of the force, the mv, okay, gets converted, given to little pieces of matter, the electrons and protons specifically, but you know, we might as well just say the atoms for the sake of argument. And now the atoms have the mv. So the mv goes from being strictly just a force to being now in a piece of matter. It's a piece of heavier mass moving a slower speed, but it's still the same force, okay? It's now in the form of matter moving. And when matter moves, that's heat, okay? So that's how what basically happens is the heat created by gravity, all right, you know, that's what it's doing. It's making things hot. So gravity makes big things hot. That's why the sun's on fire, okay? And that's why Jupiter has a bunch of storms. If you think about, you know, all the stuff moving and, you know, the red spot moving, all the swirling stuff, all of that has to be created by internal energy. Can't be created by the sun because the sun is so far away. So the sun is not producing any thermal radiation at all. So all of that has to be created by the internal heat of Jupiter. And Jupiter's hot inside because it's big and it's under a lot of internal pressure. So the idea, basic idea of, you know, a Lesage gravity is, you could just say if an object was here, okay, that clearly this force hits it because it's going the speed of light. It's, you know, a certain amount of force, and the force here, obviously it's not getting to the surface at the same time because it's moving a bunch of matter, so it's not going to get there. So there's not an equal amount of force on both sides because you're delaying the force by moving heavy bits of matter that don't move fast enough. That's a simple argument. And so the force can't be equal on this object because a bunch of the force can't get to it. Alright, and it's just that simple. It's being blocked or shaded or consumed is almost a better way to say it, by the fact that this heat is created. Now the heat isn't some sort of permanent condition because this thing is obviously radiating out to the universe, okay? It's not a sealed container. So the heat's certainly going to go back out. And so it has to be constantly fueled. And so it's constantly absorbing more energy to stay hot. It can't stay hot unless it keeps making new heat, is the simple argument. And so this never catches up. It never catches up at any one moment of time. It can't catch up. So there's always you could say it goes this way and then there's a compensating that way, but the compensating this way doesn't undo the fact that now this other force is going to keep pushing, and so it's always going to restart the push. This pushes, this stops the push, but then the push is restarted, and then it stops the push, and this push is started, So you never stop it. And so that's why things move into the earth. Now, once they do that, okay, the pressure on the inside, you can understand, gets very high. So you could argue that if there was an object I could put inside the earth, that now the only thing that matters is how much mass is on this side versus how much mass is on this side, blocking the force. And so it's not till you get to the center that those two would be equal, and then there's no gravity. So if you could hollow out the center of the earth and sit in there, there wouldn't be any gravity moving you, because both sides would be consuming the same amount of force, the same amount of heat would be created, and so you wouldn't feel any difference. The difference would be you're getting bombarded by less force, but you wouldn't feel it gravitationally. But what you're going to feel, what's going to happen is if you hollow out the center, you're not gonna last very long, because the pressure is so intense that all the atoms are now moving. So you're not going to get bombarded by the force, but you're going to get bombarded by atoms moving. Okay, so you can sort of understand that the pressure on the inside of the earth is gigantic, not because the gravity inside the earth is gigantic, it's because all the collected motion. Okay, so the MV of the stuff on the outside is high, so it has a high acceleration, but the stuff on the inside is under insane pressure from all of these. So these arrows compound, all this motion compounds, so it's a tremendous amount of mass above your head, so to speak, and an incredible crushing power. So your potential velocity is very high if you could open a pathway to go shooting out. The pressure is insanely high, so your potential velocity is increasing, but your acceleration is decreasing. If I can say it that way. I just did say it that way. So the sun is on fire. Now that's it looks impressively different than, say, Jupiter, but it's 1,000 times bigger than Jupiter. So, and then you have to get into the dynamics of what's creating, what the sun is actually doing to the matter that exists. And I guess the argument I would make is because it is so incredibly high pressure that it's actually breaking as much atoms as it is making. So it's in the constant process of just, burning up as much hydrogen or as much helium as it is creating. Okay, so they could make an argument that it's making more and more helium, but you could argue just as much helium is being consumed by the heat as is being created by the heat. So the high pressure makes it possible, the high heat makes it possible for you to do lots of chemistry, but the chemistry works in both directions. You break as much stuff as you make in the process. So it makes a bunch of heavier elements over time. So in this process, it does create an environment where a lot of stuff is banged into a lot of stuff, and so you can end up start making lots and lots of elements. And there's a certain point, I guess, where the suns blow up, okay, and turn the whole thing in reverse, and then it has to reconsolidate again by the same gravitational process. So obviously this is a hugely anti-entropy mechanism, gravity. It is the source of, you could argue, the conditions that allow for the rest of the universe to do anything, is the fact that gravity consolidates matter and creates this opportunity to create all this distortion in the field, and events like a supernova. Alright, so we'll erase this and try to not start over, but state in another way. Alright, so I guess a point I'm trying to make about heat and pressure is that if you have heat and it can't get out, okay, that it's, if it's, let's say you had a container, a tin can or something, okay, and you have very high pressure, but the high pressure can't leave. That is, the little bits are moving very fast, but they can't get out. They're just constantly reflected back into themselves. Then yes, the heat is stored as something else. Okay, the motion is trapped, but it's not, you can't detect it because it's not able to create any radiation, okay, infrared radiation that can leave this container. So the heat, in some respect, has been converted into something, it's the same pressure, right? This is the whole point, is it's high pressure in here. And that's all you have is the high pressure, all right? And if the high pressure is allowed to escape, then we see it as heat. But if the higher pressure can't escape, then we just see it as a tin can, you know. And we can understand it's got high pressure. Now the catch with the Earth, okay, and other things in space, yeah, so okay, I should have drawn this maybe another way. It's very hot in the center, okay, so that's the highest place, the highest heat. That's where the most heat is being generated, is in the very center, because that's where the most pressure is, where you have all of this motion, okay, a little bit of motion on this surface, a little still motion, motion. It's all motion. It's all MVs that are adding up, the MV of a lot of masses above something. And so again, the pressures from both sides, this crushing huge pressure, hot, because it can escape, because it does keep things moving, all right, because the pressure isn't being reflected inside the core of the Earth, it's, you know, active. And basically what you're doing is you're just saying that this heat, this high pressure, is now going to be spread as it goes out over larger and larger density of matter. So as it goes in, it's collecting more and more, and you know, one little tiny pebble hits a tiny bit of energy, and it collects and concentrates, and likewise when it goes out, it's, you know, it's turning back into pebbles. So even though the pressure in here is gigantic, the pressure out here will be tiny, you know, little pebbles moving out of the Earth, so to speak, little bits of motion. So the Earth won't look on the surface like what it is on the inside. They're not going to be the same thing because of the fact that this cycle has to transition. So the Earth is at an equilibrium, okay, over time, the same amount of heat, okay, in terms of gravity, movement of matter is going in as is going back out. And the difference is this happens in T1, the going in, and this happens T2, the going out. And we exist in T1. We exist in the T1 world of the right now. And so right now, T2 hasn't gotten to us. T2 is trying to get through the Earth, and it isn't here yet. And so we're always in that imbalance of, you know, waiting for the energy to get out. And it just takes time for it to go in and then to come back out, so to speak. So anyway, so the Earth doesn't look like a fireball, okay, even though it's a fireball on the inside, even though it has very high pressure. And you can understand, if I make something bigger and bigger, like 1,000,000 times the size of the Earth, I'm going to create more and more heat, and the heat's going to have an easier path getting out, in the sense that obviously there's going to be less and less solid matter because everything's so hot. And you know, we got lava just, you know, it's not very far, a couple miles under the ground. You know, and volcanoes are kind of evidence of the fact that there's a lot of heat inside the Earth that's just, you know, sort of dying to get out, and explosively. So that's a whole nother subject, is the explosiveness of this whole circumstance. And so what I'm arguing that's happening inside the sun is that you know, they have this theory about a strong force, okay, that electrons and protons are affected by something called a strong force, of protons anyway. and that pushes them together, some magical new force. And it's not a magical new force. It's just the fact that electrons and protons have an inverse relationship. So the simple truth is all you're doing is building, in a sense, magnets. So the universe starts with electrons and protons. You can understand that the simplest arrangement would be the typical hydrogen atom, which would be an electron and a proton in proximity. Now the trick is the typical form that hydrogen takes is this. Okay, it's two atoms stuck together. So this is what they call hydrogen. Okay, so and it's not really hydrogen, right? I mean, it's not one atom, it's two atoms of hydrogen. And so that's the form it takes, because that's much more stable. So you can understand right there that you could break that, and that would release some energy. Everything you break is going to release some energy because of the way it's put together in the first place, and that anytime you disrupt this circumstance, it's going to be able to create energy. So the simple argument is look, there's intense repulsion between these two electrons. They hate each other intensely. So the fact is, we put the electron between them, the two protons are attracted, so they can move in, get very close to each other, because they can't see each other through the electron. That's the simple idea. And the simple idea is that you can understand that's a ton of stored velocity. Okay, there's a ton of stored velocity here, because all I have to do is remove this quickly, and these two things are going to fly apart like two magnets stuck together. There's going to be a tremendous pressure, and they're going to fly apart at very high velocities. So, and that's what the sun's constantly doing, is playing with these little bits here. Okay, so it's constantly building and breaking these relationships, where it's, with the intense pressure, it's pushing things into each other, banging them into each other, and every now and then it gets this arrangement correct, and it makes one of these objects. And it might even build one of these, and it might even build a helium. It can build all kinds of them, but it's at the same time going to be breaking them, because every now and then it's going to hit this with enough force to knock that electron out, and these two protons are going to fly off. And so it's constantly making and breaking atoms. And the bottom line is it's doing it just because of all this gravitational pressure that creates all this opportunity to smash matter closer and closer to itself. So I analogize it too. I'd like to make some sort of demonstration out of magnets just to prove the point. But you can understand, if it was all little magnets, right? Little magnets, and they repel each other. Very strong repulsion, very strong attraction. How come they're attracting both ways here? Oh, there it is. Okay, so I mean, I could hold that little magnet on there, right? So let's just say that I have arranged it. I got an electron there, and I have two protons next to each other, and what's going to happen? Nothing. Yeah, right. Okay, that was a great demonstration. Anyway, these are crappy magnets, apparently. Okay, so these two are repulsive. So if I hold that there you go. So you saw that, right? Yeah. Okay. Yeah, that one magnet has just lost its magnet. All right. So so there's an electron in there holding it together. Now knock the electron out. Whoa. Lots of energy stored in there. So that's the simple principle, is that this is really, you really do have to understand charge. You can look it up on my website, and to understand how simple a mechanism that is. So if there's an electron in there, it's stable. Take the electron out, not stable. And that's the strong force. So the strong force is just charge. It's just like a magnetic force. So again, if I just took a bunch of magnets, you could understand that there's a lot of chaos between them. They'll turn, they'll do all kinds of things to, and and the fact is what this external heat is doing is putting all those little magnets jiggling until it arranges them all in little tight packages. But again, once you arrange it in a little tight package and you keep hitting it, you're going to break them too. So you're constantly breaking them and making them, breaking them and making them. And so I would argue that I don't think fission is a thing. Okay, so I don't think you can make energy with a fission reactor. It's probably never going to work. Okay, because really the game is make it, because it's pretty easy to make, right? You just stick an electron in. It doesn't take much energy to get that electron in the right place. It takes a lot of, but it releases a huge amount of energy, again, when, I can't even push these together, it's so strong. I mean, it's really a lot of force created by that electron. That electron makes these magnets are repelling each other very strongly. I just stick an electron in there. You just stick another magnet in there, and I can stick them right together, right? So I just stick a magnet in, and I can stick these two together. And then all I can do is I can, now they'll be really close, and as soon as that is gone, then, I take away that mechanism that's allowing them to get close together, and that's the strong force. The strong force is the reaction that takes place when you remove that electron. But I mean, this is Maxwellian in a sense. I mean, Maxwell's drawings are basically telling you that this is a thing you can do. I mean, obviously, if look, their own understanding of electrons and protons is isn't complicated, so they know this is a possible arrangement. And so why wouldn't you understand that? Of course, why couldn't that happen? Why couldn't an electron get between two protons and allow the protons to get incredibly close to each other? Why wouldn't that be the logical answer rather than creating some fake strong force to push them together? Now, atoms sort of, I mean, what they already know about atoms already proves this case in the sense that this is essentially what they call a neutron, just an electron and a proton. That's a neutron. So, there's when they tell you what an atom's made out of, they're really messing it all up. It's just made out of electrons and protons, and the fact is that the nucleus has electrons in it. Okay, half the number. So for every two protons, there's one electron. And so that's all the nucleuses are made out of that configuration. So the number of protons is usually going to be equal to the number of protons in a lot of cases. Obviously, with the bigger and bigger atoms, it gets messy, and you don't have exact equalities anymore. But there's no rule. It's just a tendency. And but the fact is that's the arrangement, and you can just understand that yes, if I could theoretically hit that electron with enough energy, a gamma ray or something, and knock it out of there quickly, that yes, these two protons are going to react violently to that event. And that's what we see in nuclear reactions. What are called nuclear reactions. Everything's a nuclear reaction, frankly. The whole universe is just electrons and protons swimming in a sea of bits of energy. That's the real universe, the only one that's doing anything. And all of this crap is just an extension of those processes. It has to do this before it can do this. So this is trillions and trillions of these interactions. Electrons and protons bumping around, shooting, reflecting forces at each other, absorbing and reflecting. That's the only thing that's taking place. Alright, might be enough for this draft video. So yeah, it's not completely as tight as I'd like it to make it. So it's good practice, and I can work on it some more, and blah blah blah. Something like that anyway. So till the next time and such, and so forth and whatnot.